Good morning. So we'll finish this second order homogeneous ODE, give you a few examples, and then we're going to talk about an application of this homogeneous second order ODE, which is we call free vibrations. Okay. So first of all, just a quick review. I forgot to print this thing for you guys. I'll bring it to next time. So basically, it's a page of a summary from our lecture notes. Okay. It could come in handy when you are solving this kind of differential equation. All right. So here's a summary. Second order homogeneous ODE, and I'm trying to make it more general. So previously, the example I did is I used A as 1 here, right? So well, I'll just use A at here, okay? Yeah. So sometimes you do have A here, but it doesn't matter. If you divide A by both sides, that can be normalized. Okay, so when you have this kind of second order homogeneous one, because this is 0, that's what we call a homogeneous. First step, write down the characteristic equation. Okay, and that's very easily done. And just basically form a quadratic function based on the second order one here. Okay, so this is what we call characteristic equation. Then the solution for this characteristic equation is lambda 1, 2 equal negative b plus minus b squared minus 4ac over 2a. Right, that's general solution. So now here's a table. You need to look at the value of the b squared minus 4ac, okay, and to find out that this corresponding cases in this table. 3 different cases, basically. Okay. Yeah. First case, when you have 2 distinct roots, that's your general solution. Second case, when you have 2 repeated roots, this is your general solution. Last one, we have 2 complex conjugate roots, and this is the general solution. Okay. Yeah. So basically, here is your guideline. Here it's very straightforward now. The value of alpha and beta here for the third case regarding the B and A is this. So I don't want you to remember these formulas here, okay? I don't want you to remember the formula. I want you to know basically how to get to each one of the cases. Right? Any questions? All good? Yeah. So let's take a look at a few examples here. So here's a second order ODE with initial condition here. Okay. And by the way, because this is second order one here, so the initial condition at here, you need 2 initial conditions now. Okay. So when we solve first order differential equation, when we have 1 initial condition, that's enough because there's only 1 unknown constant c, right, in the solution. But in this particular case, if you look at our general solution, we have 2 unknown constants there. So chances are we need 2 equations. Basically, we need 2 initial values or initial condition to solve for these things here. Okay, so here is this equation here. So first step, write down the characteristic equation. There, right? Okay. Okay, so then from this on, okay, I think you can, different people have different skills now. So if you don't have the training of separating this one into factors, so you can always go back to the formula here, right? You can always go back here. But if you had a training before, when you look at this one here, often in time you can see it directly. You can separate this one here into what? Like this, right? You can see it directly like this. Because 2 equal to negative 1 multiplied by 2, and 2 by negative 1 is 1. So I can write it into the two factors here, right? Yeah. So this gives me two solutions. Okay, and both of them are real numbers, right? So which means I have two distinct real roots. Then my general solution, right? The general solution. So you don't have to write. You don't have to write every time. The general solution is y equal to c1 e lambda 1t. Lambda 1t is -2, and c2 lambda t. So lambda is 1, and it's t here. Okay, it's very straightforward. So good. Okay, so now let's try to find a value c1, c2 based on the given initial conditions. Okay, initial values. So to find this one here, I have y of 0 equal to 4, and y prime of 0 equal to -5. So I guess I need to calculate y prime first. Okay, so this is a general solution. The derivative of y, let's see, what does that give me? -2 c1 and this plus c2 this, right? Okay. That's y prime. Okay, so then I'm going to apply this initial condition. So y of 0, apply this y of 0. Y of 0 meaning at t equal to 0. So y of 0 equal to 4. Apply t equal to 0, plug the t equal to 0 right here, t equal to 0 right here. So I get c1 plus c2. Okay. Yeah. Then next one, y prime of 0. Y prime of 0 is -5. Apply t equal to 0 here, at here. So I got -2 c1 plus c2. So two equations, two unknowns. So you can easily solve for c1, c2, which is 3, which is 1. Okay. So that's a typical approach solving an initial value problem. Okay, for second order ODE here, differential equation. So in the end, you can see, okay, so my general solution for this particular initial value problem is y equal to 3 of this multiplied by this plus this. Okay. Yeah. Yeah, so actually I wouldn't call this general solution now. This is a particular solution. Right, it's a particular solution. Yeah. Because it's out of the pool, right? Yeah, for a specific value of c1, c2. So let's take a look at another one here. Y double prime plus y prime plus 0.2 pi y equal to 0. Okay, so in this case here, same thing. Lambda square plus lambda plus 0.25 equal to 0. Okay. So what do you think of the value for the lambda is? Without using your calculator, can you see the solution for the lambda from here? Come again? Pardon me? 45? 45? No. See, this is 0.25, right? 0.25 is what square? 0.5 square, right? So this guy is actually just this. Okay. So my solution is this. So in this case here, which case are we dealing with? Second case. Right. So you got two repeated roots. Okay. And lambda is this. So in other words, your general solution y is C1 e negative 0.5 t plus C2t e negative 0.5 t. Okay? So look at this case here, right? When you have two repeated roots, your solution is this. Okay, so C1 plus C2t e lambda. I just multiplied it out. Okay, so that's your general solution. Okay, so I guess this one, that's it. It doesn't have any initial value. That's okay. Yeah. So I just want to show you a different cases. And let's see another one here. Okay, so this one you might need to use a calculator, or you're still using a hand calculation, still fine. Okay, so second order and characteristic equation. Okay, so characteristic equation is this. So this is not that straightforward now. You probably won't be able to see it through that easily. So you may need to plug these numbers into this formula here. Okay, into the formula. Okay, over here. Okay, into this. Okay. So in my case here, this is 2 at here, negative 0.4 plus minus 0.4 squared minus 4 by 9.04. Right? So this one, you might need to use a calculator to calculate this. It looks scary, but actually it can be. First of all, it's very easy to see this is a negative number here, right? Yeah. So what we have here is two complex conjugate roots, which is the case number 3. Okay. So if you use your calculator to calculate this one here, the term at here, which basically is this. Okay, negative 9. Okay. See, 0.4 squared is 0.16, right? And then 4 by 9.4 by oh yeah, actually negative 36. Yeah. Oh, I have some errors here maybe. Yeah, you're right. I got some errors in my lecture notes there. So negative 36. Okay. Just double check just a sec. Yeah. Yeah. Okay. So 4 by 9.04 is 36.16. So that 0.16 got cancelled. Only 36 left. Okay, so then this guy equal to negative 0.4 plus minus j, what? 6, right? Was that right? Yeah. Divided by 2. Okay. So you have, then keep going. Okay. Point negative 2 plus minus 3, j3. So you have two complex conjugate roots. And we have case number 3. So let's take a look at case number 3. here's alpha plus minus g beta, right? In our case, my alpha is negative 0.2, my beta is 3. So I can simply form my general solution using this formula right here. Okay? Yeah. So 3 things here, and I recommend you memorize this by heart. Okay? Yeah. I might give you this as a final exam. I'll give you the formula sheets. This might be in the formula sheets, might not be. Okay? But in the meantime, when you practice your assignments, okay, try to remember this one now. So this is my alpha, and this is my beta. Then general solution y equal to e alpha t cosine beta t plus an a at here plus a constant b and sine beta t. Okay, so that's the general solution. So whenever you have a complex conjugate roots there, chances are basically you have oscillations, okay, because of sine and the cosine, the presence of sine and cosine. Now let's take a look at a special case here. Okay, you see this term here 0.4 here, and this is some numbers that are here. Now what if I have a second order differential equation like this? Okay. So here is another example. This is basically what we're going to talk about next. If I have a second order homogeneous one, y double prime plus omega square y equal to 0. All right? Yeah. Which means what? Which means the coefficient for the y prime term is 0. So there's only 2 terms. There are only 2 terms here. So then in this case here, if I follow my procedure, so the lambda square plus omega square equal to 0. That's my characteristic equation. The solution for the lambda is positive negative j omega. Okay? Yeah. So then my general solution is y equal to a cos omega t plus b sine omega t. Right? Yeah. If you recall that in the last lecture, I mentioned that I didn't do the proof, but I did give you the results here. When you have 2 sinusoidal signal adding each other, okay, with the same frequency, basically, you can combine them together, right? You can combine them as a squared plus b squared cosine omega t, then minus a phi here. Okay? And the phi is related to a and b. Is a tan inverse b over a, something like that. Okay. Yeah. Now, essentially, what this tells you, what this guy tells you is, when you have 2 sinusoidal adding each other together, you end up with basically another sinusoidal signal, and the frequency of the signal here in this particular case is just omega, right? Just omega here. Now, if I look back at my second order ODE here, where is that omega from? It's from the coefficients of this y term here, right? Coefficient y term. Does that make sense? Okay. So basically, when you have a second order ODE, and maybe there's some terms of something like y prime here, right? But however, okay, as long as you know that you have a complex conjugate roots, then you know that you have a sinusoidal response, and there are certain frequencies associated with the response, and where the frequency is from, that frequency is related to the coefficient of this y at here. All right? Yeah. So this is basically naturally bringing us to the next topic here, which is what I want to talk about today, the application of this second order ODE here, which was what I call it is a free vibration. So sometimes we also call it harmonic oscillator here. Okay, so let's take a look at this phenomenon here of free vibration. In your 3rd year course for mechanical, there is a course called vibration. So lots of these results that are here, you're gonna probably learn it again or being reviewed. So first of all, the concept so-called free vibration. Free vibration basically, why is it called free? the meaning at here is because when I have a second order, let's say that ODE here, AY double prime plus BY prime plus CY, here 0, right? Here 0. This 0 here bring this meaning of a free. Okay, so the vibration is not under influence of external force. It's purely because of the initial conditions. Okay. So I'll give you I'll use the example of mechanical mass spring damper system to illustrate this thing here. Okay. So number one, okay, we're going to talk about is so-called undamped system. So undamped system, what does that mean is this. Here's a mass spring damper system, but I don't have any damping. So there's only spring there. Okay. So the system doesn't have any friction. So in this particular case, it's what we call undamped system. So there's no damping, and there's no external force, just the spring and the mass, right? Then we have derived the equation motion for this guy here, for general one here. Then for this particular case, it's just to mx double prime plus kx equal to 0, right? Because I don't have that damping term. The damping term is bx dot, right? So that term b is 0, so that term is gone. So what I have here is a second order ODE, and it's homogeneous because there's no external force in it. Okay. So now, if I make a little simplification at here, if I divide it by m, so what do I get? So I got this guy here, right? I got this. And for this particular one here, if I compare this one with the last example I had here, that's exactly the same format, isn't it, right? That's exactly the same format here. So then, what I can say now is, for this particular one, the lambda is positive negative jk over m. So that's the lambda value. Now, in this example here, I use the symbol omega square here, right? So basically saying, meaning the omega at here, it's what value? It's this square root of k over m, right? So the omega is k over m at here. So this omega here actually is the frequency what we're looking for, because we know that the general solution for this undamped system is x of t equal a cosine, okay, is k over m t plus b sine k over m t. Right. So if I replace this square root of thing with omega, so I basically get a cos omega t plus b. Yeah, I'll let it equal to omega n here. Okay, equal to omega n. Okay, I'll let it equal to omega n here. So then that's your general solution at here. This omega n at here, there's a name associated with it. This is called natural frequency. Okay, so this guy here is called natural frequency. Okay. It's the natural frequency of the system. Okay, of the system. What system? This system here, right? So natural frequency is a very important concept. Every system has a natural frequency, and some system has more than one natural frequency. It probably has 2 or even multiple, or 3, even more. Okay. So for this system here, there's only one. That's just one natural frequency. What the importance about this natural frequency is because you don't want to work the system under the natural frequency. So the idea is, let's say the building has a natural frequency, but maybe it's very high, right? Maybe 100 kHz, who knows? Okay, but you don't want to excite this building, okay, to that kind of natural frequency, because when the thing is working under this natural frequency, and usually what we call it's a harmonic motion, and when that happens, generally there's some bad thing will happen. Yeah. Basically, the thing will start to vibrate very, very large amplitude, so some damage could be done, right? Yeah. So same thing to our body, right? We also have our own natural frequency, and you don't want to work yourself under this natural frequency for a long time. Okay, so for a little short time, it's okay. So remember this concept of natural frequency here. And where is it from? It's basically, it's from the coefficient of this term in here, right? Of this. Okay, so that's, if you can remember this fact here, so basically you have a second order differential equation, you can immediately extract the natural frequency out of this second order equation here. Right? Yeah. Okay, so if I go back to this solution in here, okay, suppose that I have initial condition. So let's say my initial condition is this. So I have an initial position, I have an initial velocity. Okay. And by the way, because the system doesn't have any external force input, right? Doesn't have any external force input. So if my initial position is 0, if my initial velocity is 0, what happened to the system? It doesn't move, right? Yeah. So you want a system to move, you have to give the system a slight initial condition, either here or here, right? Yeah. Okay. So let's see if this is the case here, and what would be the value of A and B corresponding to these two initial conditions? All right. Yeah. So I'm not going to solve this anymore because this is quite simple. You just basically plug in initial condition, take a derivative, and just solve it as usual, right? But you will see that the value of A corresponding to the given initial condition here, A is basically C. And the B value is x prime 0 root m over k. Okay, not k over m, it's m over k. And which is D multiplied by 1 over omega n. So that's the connection between the A and the B and initial condition x of 0 and x prime 0. Okay, yeah, that's A and B here. Now, what we really want to see here is, okay, I really want to interested is in the graph of this x of t here. So I'll give you a general graph of this x of t here. Here's x of t here. Because there's no damping, then as you can see from the solution in here, the x of t essentially just gonna keep oscillating, right? Just keep oscillating here. So a typical look at x of t is probably like this. Okay. So it's a sinusoid. Typically look like this. Okay. So when you look at the response of this here, and I need you to understand, okay, just basically look at this response here, understand a few important facts. Okay. Number one, you can tell from the graph the associated omega very easily, right? By measuring the period, then you can get this omega, right? Number two is you can also get this initial condition by looking at this graph right here. Because why? Because this particular value right here, this is basically where it starts. This is your x of 0. Okay, this is x of 0 here. Okay, yeah. So, for example, if your initial velocity is 0, okay, initial velocity is 0, then this b term will be 0. So all you're left with this term here, right? All you're left is this term. Okay, yeah. And the other fact is this: when you draw a line, the initial starting at here, when you draw a slope, okay, when you draw a slope, okay, at the beginning of this sinusoidal curve here, this slope right here, that slope give you this x prime of 0. Okay, give you x prime of 0. The reason is because if I take the derivative, of this solution in here, okay, take a derivative of this solution, you can see that the derivative solution is negative c omega n sine omega nt plus d1 over omega n multiplied by omega n cosine omega nt. Okay, so that's the derivative of this term here, right? By plugging a and b into this one here. So then I can simplify this just slightly, which is c omega n sine omega nt plus d cosine omega nt. Okay, cosine omega nt. And we're talking about initial here. Initial here, that means the t value initial is 0, right? So at the t equal to 0, you plug a t equal to 0 over here. What do we get? We get x prime 0 is d here, right? You know that, yeah, that's exactly what we want. But x prime meaning is the derivative. X prime derivative meaning is the slope. Basically, here represented the slope at this t equal to 0 point. So the curve depends on your value of x prime, right? The curve basically determines where to go. For example, in this case here, I must have what? I must have a positive initial velocity because it's going up here. Okay? If you have a negative initial velocity, so that sinusoidal curve should go down. Right? So what if I have initial velocity 0? What would you expect the beginning of here? It's a peak, right? Yeah. Good. So that's when you look at the response of a system. Okay. So then you would be able to identify a few of these facts here. Okay. Yeah. So that's free vibration. This is actually a simple one. The second one here is this is an undamped response. So the second one here is free vibration, but now with viscous damping. So basically, it's a damped vibration now. Okay, so with the viscous damping, I think we know what to do. So we're going to add spring and the damper into the system. The equation motion is mx prime t plus bx prime t plus kxt equal to 0. Right? That's the equation motion. Okay. So I'm not using any numbers here. Okay. In the past, I know some students got confused when you don't have any numbers, just the symbols. Particularly this portion here. Okay, this portion. You're gonna see lots of writings here, no numbers. But you need to remember what we're dealing with is a general case here, right? And it's actually not any difference from any differential equation with a number. So m lambda squared plus b lambda plus k equal to 0, characteristic equation. Solution for this one here is negative b plus minus b squared minus 4mk over 2m. Okay, so now I'm gonna instead of using mbk, so we're gonna associate with a convention that everybody has been using. Instead of using mbk, we're gonna use a slightly different symbols here. Okay, so I'm gonna define a couple of things here. First of all, we're going to define our natural frequency as before. So that natural frequency is square root k over m. So this is reading per second here. So second of all, we're going to define a so-called a damping ratio. But before we define this damping ratio here, there is a so-called critical damping constant. So that B is a damping constant or damping coefficient. So now we have a so-called critical damping constant. So this particular value is equal to this one here. Okay, this is defined as BC equal to square root 4mk. Basically this term here. Okay, why is it critical? See here, right? See, this is the square root b squared minus 4mk here, right? So you can see now what differentiates the three cases is b squared, whether b squared is greater, equal, or less than this 4mk. So we're going to set this square root 4mk as a special value. And that special value, we call it so-called critical damping constant. Okay, it's critical here. So that equal to 2 root mk. So the last one here we're going to define is so-called psi here. This term is called damping ratio. Okay, it's called damping ratio. So the damping ratio is defined as this. Damping ratio is defined as a damping constant, which is the B value, divided by the critical damping constant. Okay, so that's psi here. And this is a B over, so this damping constant is B. Critical one is defined as this guy here, right? So 2, this. So that's damping ratio, right? Damping ratio. So now you actually probably see the meaning of this now. So damping ratio essentially is a ratio between where? Between this B and the square root 4mk. So essentially it's a comparison between this B squared and 4mk here. Okay? Yeah. So the zeta, the cosine here, yeah, I think this is cosine. If sometimes you write one more term here, it becomes zeta. So anyway. Okay, so now I'm gonna use this omega n and zeta here to talk about this second order ODE now. Okay? Yeah. So then what happens is this m lambda squared plus b lambda plus k, instead of writing this in this one here, if I divide it by m, okay, then this is lambda squared plus b over m lambda plus k over m equal to 0, right? Okay, and this one here, I can rewrite it using this new definition of omega and zeta. So omega is this guy here. Basically, this is what? Omega, this x here. This is basically omega squared, exactly. So that's omega squared, omega n squared, that's I call it omega n, right? And x prime here is b over m. If you do a little manipulation, this is equal to 2 zeta omega n. Okay, so you see 2 zeta, 2 by this, by that, okay, 2 by this, by that. You're going to get back this b over m. Okay, you're going to get back this b over m. All right, so now you have this new, not a new one, but it's just, okay, a different kind of expression, right? Using a slightly new set of symbols, okay, new set of symbols here. So then, what I'm going to do is I'm going to essentially go over the same steps of solving second order ODE. So how many cases do we have? 3, right? So I'm going to talk about the 3 different cases, okay, based on the values of this zeta here. So previously the 3 cases based on what? Based on this relationship between b squared and 4mk here, right? Now the relationship between b squared and 4mk, it's directly related to which one? To this so-called damping ratio. Okay? Yeah. So case number 1, okay, is when your zeta is greater than 1. So when zeta is greater than 1, which means what? This b is greater than this term. Right? So the numerator is greater than the denominator, which also means my solution at here, basically the solution at here, the square root term, the term on here is greater than 0. So basically means you have what? You have 2 real roots, right? You got 2 real roots here. Now for this particular case here, what I call this overdamped, okay, overdamped response. So You need to remember here, we're not doing anything new, okay? The only reason I'm doing this one here, I'm trying to basically associate this those seemingly mathematical expressions to practical mechanical response or system history here, right? So you'll see why we call it overdamped response. But for the time being here, remember that when damping ratio is greater than 0, it's going to be called overdamped response. So why is it called overdamped response? It can be explained through this general solution here. So what is the general solution? General solution is because when this one here, you have two distinct roots. Two distinct roots. When you have two distinct roots, your solution is E lambda 1t plus C2 E lambda 2t. Okay? That makes sense? Yeah. So what is the lambda 1 and lambda 2 here then? So lambda 1 and 2. Okay. So lambda 1 and 2 is this guy here. Okay, it's this. Now I'm not going to use BMK for this one here. I'm going to use my zeta omega n, okay, to express the lambda. So just slightly here, the lambda in terms of the zeta omega n is this. Okay, this is my two lambdas. Yes.
I'm kind of lost after case 1.
Lost at where?
After case 1.
After case 1. I haven't started case 1. You mean before the case 1?
Yeah. What are you doing? I didn't get it.
Yeah. What I'm doing here is I'm trying to show you. Instead of just solving, right? This is just solving here. Basically, those examples just solutions here, right? If I don't tell you anything like that, what do you have? You're just solving it. Is that right? But what I want to show you here is, instead of just solving it, I want you to observe, what's the mechanical meaning in it here. Okay? So, first case, this is basically the first case when you have two distinct roots. Now I'm giving a new meaning here. I'm saying this when you have two distinct roots, and when you have a mechanical system like this, actually not necessarily mechanical, even if it's an electrical system, you can still have the same kind of meaning here, right? And when you have this zeta value greater than 1, we're going to have a so-called overdamped response. So you just wait a second here. Why is it called overdamped response here? Okay? Yeah. So I just skipped one step here. Instead of using BMK, I'm using zeta omega n net here. All right? So here's lambda 1 and lambda 2 here. Now I want you to observe what is the lambda 1 and lambda 2 values, right? So first of all, you need to understand real systems, so all the parameters are positive numbers, right? So the m, b, k, they're all positive numbers, which also means this omega n and zeta, they're all positive numbers. So now when I look at this expression in here, so this term must be less than 0, right? So that means lambda 1, if the lambda 1 is negative, this minus that, then lambda 1 must be, if this is lambda 1, so the lambda 1 must be what? Less than 0. Okay? How about lambda 2? Okay, how about lambda 2 at here? So if I look at lambda 2 here, is the lambda 2 going to be greater than 0 or less than 0? So if this is a negative number, this is a positive, right? Whether it's greater than 0 or less than 0 depends on the absolute value of these two. If you look at the second one here, what's the value of zeta? Zeta is greater than 1. So that means the second one here, right? The second one here, if I don't change the first one, the second term must be less than this one here. You see that, right? So this term must be less than this term. Why? Because I don't have minus 1 here, and this has minus 1 here, right? So square root of zeta squared must be less than square root of zeta squared minus 1. So this term less than this, meaning this term must be less than this term, right? And this term here is essentially equal to what? 0. So which means lambda 2 is also less than 0. So both of those roots, lambda 1 and 2, are less than 0. If both of them are less than 0, you go back to this equation in here. When you have two exponential functions, both have a coefficients here less than 0, what do you expect to have? If I just have 1 here, less than negative t, what do you expect to have? It's exponential decay, right? If you have a 2, what do you expect? It's still going to be something like this, isn't it, right? So, which means this x of t here, right? So this x of t is kind of exponentially decay here. Okay, it's massive decay here. So the question I ask you, will you see any oscillations? You won't, right? You won't see any oscillations. All you see is for this x of t, it's probably starting from initial value, probably go back to 0. And not 0, go back to approach to 0 here, right? So this is why we call it overdamped. So no oscillation. No oscillation is called overdamped response. Okay? Now, do you see the meaning of what I'm doing here now? Yeah. Okay, so you're not just solving it. So you're saying it, oh, I got an overdamped response, right? I guess 30 minutes, that's what I want to see. So, is that good? So I have a couple of more, 2 more cases here, but they're relatively clear now. All right? Yeah. So we'll talk about next time.